This session is about using SEEP-W. In session 1 we are going to concentrate on steady state analyses, and then in session 2 we will migrate on to transient type of analyses. The first question that we might ask then, what is the purpose of a seepage analysis? Well, fundamentally, the purpose of a SEEP-W analysis is to simulate seepage or water flow through soil. And we want to do this both for saturated and unsaturated conditions. The result of the SEEP-W analysis might be various objectives. The first one is that we might be interested in the quantity of flow or discharge. That is, we are interested in the flux. In many civil engineering projects, we are interested in pore water pressure distributions. We need to know the pore water pressure distribution for a stability analysis, and we want to use the SEEP-W results in slope-W. We need the pore pressure in order to get at the shear strength if we are going to use effective shear strength parameters. Sometimes we may have excess pore pressures as a result of external loading due to the building of an embankment, for example, and then we need to know the pore pressures in sigma W in order to compute volume change and consolidation, and we also need to know the effective stress in the ground because we know it is effective stresses that control volume change and shear strength. Sometimes we may be interested in the water velocity and in the pathway. If we can determine the velocity and pathway with SEEP-W, we can reuse the results in CTRAN-W to simulate the migration of a contaminant, for example. Pore water pressures then. This is one of our primary interests. We want to know the distribution of the pore water pressures. Here we have an illustration of perhaps some infiltration of rainfall, and we have perhaps some regional groundwater flow, which produces a phreatic surface here. And we want to know the pore pressure distribution both in the saturated zone here and in the unsaturated zone. To those of you who attended the slope-W sessions, you will recall that we could define the strength due to suction and use that strength in a slope-W analysis. In this case, the rainfall infiltrating into the ground may affect the suction and therefore affect the pore pressures and indirectly affect the effective stress and the shear strength. And as a result, stability up in the unsaturated zone is every bit as much interest as to stability at a deeper level where we may in fact encounter the saturated zone. So one of the primary reasons that we want to do a SEEP-W analysis is we want to define a pore water pressure distribution, and once we know the pore water pressure, we can define the shear strength both in the saturated and unsaturated zones, and then once we know the shear strength, we can use this in a slope stability analysis. Sometimes we want to know flow rates, or we want to know the flux. In SEEP-W, we can determine the flux across a flux section, as we will see later on. So although we do not do this all too often, but sometimes it is of interest to know the quantity of the seepage losses. Here's a diagram illustrating when we might want to have an understanding of the water velocity and the pathway. And here is a contaminant pond, and leakage from this contaminant pond, we would like to know the pathway that a molecule of water might follow, for example, and the rate that it arrives at a particular point. So we want to know velocity and pathway, and then we might be able to model a contaminant plume migration. All of you who have taken an introductory course into seepage have likely been taught seepage in terms of a confined problem and an unconfined problem. In this situation here, the flow under a structure around a cutoff, this would be classified as a confined problem, and flow through a homogeneous dam would be classified as an unconfined problem. When we use a saturated, unsaturated formulation, it removes the need for this categorization. As you will see in SEEP-W, we do not need to categorize the problem between confined and unconfined. When we consider the saturated and unsaturated conditions both in the same problem, there is no need for this categorization, which turns out to be extremely convenient, particularly as you will see when we move into transient analyses. To use SEEP-W effectively, it is essential to have a clear understanding of some of the key fundamentals. These fundamentals are Darcy's law. We need to have a good understanding of Darcy's law. It is very useful to have a mental picture of the basic finite element equation. You do not need to know how to derive this equation necessarily, but to have an idea of what the equation looks like is very useful. It is absolutely mandatory to use SEEP-W that you have a clear understanding of the definition of the total head. We usually use big H for total head. Then we must have some idea about the soil's ability to store and release water. Soil acts a little bit like a sponge sometimes. It can absorb water, but water can also drain out of the soil. And the soil's ability to store water and to release water is fundamental to effective use of SEEP-W. Related to this, we need to have a clear understanding of the effect of suction or negative pore water pressure on conductivity or permeability. Traditionally, we have talked about hydraulic conductivity or the coefficient of permeability as a constant. This only applies for saturated conditions. What we will see is that when we move into unsaturated soil, the conductivity is no longer a constant, but the conductivity now becomes a function of the pore water pressure. So this is at the heart of a SEEP-W analysis if we want to consider both saturated and unsaturated flow. So here's Darcy's law, and it is a very basic, simple law. Fundamentally, it says that the specific discharge is proportional to the total head gradient. I is the gradient. The constant of proportionality is the hydraulic conductivity, and it is the material property. Now in SEEP-W, we use Darcy's law both for unsaturated and saturated conditions. It is the same law for both unsaturated and saturated flow. There is quite a bit of literature on this, that this is a valid thing to do. I will not take the time here to discuss it further, But it is useful to know that we make this assumption and use this equation throughout the whole domain, whether the flow is saturated or unsaturated. So Darcy's law is at the heart of SEEP-W. Here is the partial differential equation for flow in a domain, and you have likely seen this partial differential equation. Looks rather ominous, but it is actually not that difficult to understand. Fundamentally, change in h over x, here this is the gradient I in the x direction. This is the gradient in the y direction. These are the material properties, Kx and Ky, hydraulic conductivity or coefficient of permeability. This is what is known as a source or a sink term, which will become clearer later. It is a form of specifying what happens at a point or what happens along the boundary. I will erase my highlighting here. So what this equation says, that we have the rate of change. We have the rate of change of the gradient in the x direction. The point is that it is the rate of change with distance within the domain of the gradient. It's the rate of change with distance of the gradient. And we have the rate of change of the gradient in the y direction within the domain. The rate of change of the gradient, or the amount of flow, plus what happens on the boundary, is equal to the rate of change of the volumetric water content with time. This is the volumetric water content. Notice that it is volumetric and not gravimetric water content. So, in the end, it's the change in the volume of water within the soil with time. Now, as we will see, that this term on the right here is only required for a transient analysis. So to summarize then, the rate of change with distance of the gradient in the x direction plus the rate of change of the gradient in the y direction plus some heat sink or source term or a boundary condition is equal to the rate of change of the volumetric water content with time within the soil. As I noted right at the start of this session, that we are going to concentrate here on steady state conditions. And what does steady state mean? Steady state means that the flow into an elemental volume of soil, the flow in is equal, I'll start over here and erase my highlighting. The flow in is equal to the flow out. That is the meaning of steady state. In other words, the volumetric water content does not change in the soil. There's no additional storage or there is no additional water released, and consequently the right-hand side of the equation turns out to be 0. Let us look at the special case then of an isotropic homogeneous condition. Let us say, for example, that Ky is equal to Kx. Consequently, this would be Kx, and this would become Kx as well. We could take the equation and we could multiply both sides by 1 over x, k rather, 1 over k, 1 over k, over k, and as a result k would cancel out, and we are left with this equation here. And as you are likely all aware, it is one of the most fundamental equation in physics, known as Laplace's equation. What is interesting about this equation, that when we have an isotropic homogeneous condition, that the pore water pressure distribution is not a function of the material property. So many cases you will encounter when the pore pressure distribution is not a function of the material property. So the pore water pressure distribution is not a function of K. And many times, for example, the flow under a cutoff wall, for example, the pressure distribution that we obtain is not dependent of the conductivity that we specify. This is a very useful observation, and that we do not need to spend a lot of time in refining the conductivity we use for an analysis if we are interested in pore pressure distribution. If we are interested in quantities of flow, then clearly we need to know the conductivity quite accurately. But if we are only interested in pore pressure distribution, then any rough estimate of the conductivity is likely more than adequate. Moving on then to the definition of total head. SEEP-W is formulated in terms of total head. Total head is the primary unknown, and it is the value that we solve for when we solve the finite element equations. So total head, big H, is equal to pressure head plus elevation head. Pressure head is pore pressure divided by the unit weight of water. So this is pressure, and this is the unit weight of water. And this term here is often referred to as pressure head. Why is the elevation? And as we will see time and time again, when we specify boundary conditions, we must specify the total head. We cannot specify pressure head very often. Sometimes under special conditions we can, but we need to specify along the boundary the total head, which is a combination of pressure head plus elevation. So the boundary conditions we specify always have to be specified in terms of the y-coordinate or the elevation. So let's look at total head in the context of this very simple example. And we have some freestanding water on this side of the dam, and we need to specify the boundary condition along this edge here. And the boundary condition, we are going to specify it as a total head. We notice here that the elevation is 6, so y is equal to 6. The pressure head is equal to 3 meters of water. Therefore, the total head boundary condition is equal to the pressure head of 3 plus 6 meters of elevation is equal to 9 meters. On this side here, we know that the water table is at the surface, so we need to define a boundary condition along this edge. Here, the total head is equal to the pressure head plus y. The pressure head is 0 plus the elevation is 6. Therefore, the total head is equal to 6. An illustration of defining total head. And as you will discover, and you need to have very firmly in your mind, is that flow always occurs from the high head, 9 to 6, in this particular case. To repeat, it is incredibly important to have firmly in your mind that flow is always from the high total head to a lower total head. Flow is not necessarily in the direction of pressure changes, it is in the direction of total head changes. Now let's look at total head definition in a slightly more complex case. And we have a water reservoir up against the face of this dam here. And we need to define the boundary condition along this edge of the analysis domain. And the question is, what is the right boundary condition to specify on that edge? Well, let us look at this point here. This example is in terms of feet. The total head is equal to the pressure head plus the elevation is equal to a pressure head of 0 plus an elevation of 40, so the total head is 40 feet. At the toe of the embankment here, the total head is equal to the pressure head plus the elevation. The pressure head is 40 feet plus the elevation is 0, therefore the total head is 40. Now this is extremely convenient that even though the pressure changes along this face, we can specify one boundary condition along this face where the head is equal to 40. The total head is the same everywhere. We need a special type of a boundary condition to simulate this tow drain here, but we will get to that later on in the presentation. Moving on to the basic finite element equation then, and it is very, very simple, and the equation looks the same for SEEP as it does for sigma, as it does for CTRAN, temp W, Vados W, that's always the same. We have a matrix of element properties here. This matrix here includes material properties and volume or area. In other words, the size of the element. H is known as the vector of the primary unknowns. It is this vector that we want to solve for throughout the whole domain. On the right hand of the equation, we have a nodal flow vector, or more generally, it is known as the forcing vector. It is the amount of flow that, for example, crosses the boundary of the domain. Sometimes this nodal value can be specified, other times the total head is specified. What is so important about understanding this simple equation is that if Q specified, H is computed. If H specified, Q is computed. And time again, when we define boundary conditions, it is important to recognize that if I specify the head, I will compute a flux, Q. If I specify Q, the flux, I will compute a head. And as we will see, when it comes to defining boundary conditions, we only fundamentally have one of two choices available to us. We either specify a total head or we specify a flux rate. And so once again, I urge you to have this little equation in your mind when you do seepage analysis. And when it comes to applying boundary conditions, always ask yourself, if I know the head, then I will compute flux. If I specify the flux, I will compute the head. I cannot specify both flux and head. That is not a possibility in SEEP-W. So I only have one of two choices when it comes to specifying boundary conditions in SEEP-W. There are always basically four components to a finite element analysis. The first one is geometry in space. The second one is material properties. The third one is boundary conditions. And when we do a transient analysis, we have to say something about temporal integration. We have to say something about time stepping. How are we going to march forward in time? In a steady state analysis, we do not need number 4. So in this session number 1, where we are concentrating on steady state analysis, we will only deal with 1, 2, and 3. Now, you will notice that we have entire chapters in our SEEP-W engineering books on geometry, material properties, and boundary conditions. Once again, this is fundamental to any finite element analysis, that you basically have 3 components for a steady state condition: geometry, material properties, and boundary conditions. And when we move on to transient analysis, we have one more item, and that is how are we going to step forward in time during the flow process. Just one last quick comment about these finite element basics. Our human nature is such that we tend to spend most of our time on the things we know the best. And so we often know the most about geometry, and we tend to spend a lot of time on the geometry. But spending a lot of time on the geometry does not do us much good if we don't have a good understanding of material properties and boundary conditions. So when you do a finite element SEEP-W analysis, you need to spend most of your time not on the geometry, but on the material properties and the boundary conditions. I will come back to this and talk further about this later on in this SEEP-W session. This then brings us to the end of a very high-level view and discussion of some of the very basic issues in a SEEP-W analysis, and it is to repeat, to use SEEP-W effectively, it is very worthwhile to have a clear understanding of some of these fundamentals.